Welcome to Digital System Implementation. My name is Bob McLeod. I can be found in E3416. Some more contact information, and just a note that if you want to find me, come to the lab. I'm rarely, if ever, in my office. These are the classes and lab schedule for this year, or approximately Tuesdays and Thursdays, 11:30 to 12:45. The room last year is E2304, but could change, and I'll let you know if it does. But if you're reading this, you're watching this, I guess it doesn't matter. The labs are in E3528, and that was the TA from last year. The dates are important. These are the dates of this year's labs. Officially, they don't start till September 26th, but I would highly recommend you starting on September 12, or you won't get the labs done. Some comments here. The notes are all online. Recommended reference book is Fundamentals of Digital Logic with the Verilog Design by Brown and Vranacek. Excellent book if you want to acquire a book. With respect to the marking, the assignments will be approximately 5% of the course, may be sent to you on short notice. The feedback is typically just a pass or an F, and it is your responsibility to see what you did wrong. There's also in-class assignments. How you find out what you did wrong? Well, you can ask a colleague, a classmate, and certainly feel free to ask me. Laboratory is 25%, and I'll discuss that in a bit more detail later. Midterm test 20%, final exam 50%, and these are within a plus or a couple of minus a couple of injury points. With respect to the labs, you're responsible to complete many labs from the Altera University Program website during the term. These can be the first 9 Altera Digital Logic labs, for example. And these would be done roughly 3 per lab period to complete them by November 1st. And that would be for a total of 2/3 of the total lab marks. At that point in time, you could complete 3 labs from Altera's Computer Org or Digital Systems course, or complete a project of your choosing that would comprise the remaining 1/3 of your marks. If you get 5 labs done, your maximum mark is 1/3 of the total lab marks available, and you get an incomplete, in fact, if you don't complete the first 5 labs. This sort of summarizes it a bit more pictorially. Labs 1 to 5, if they're not completed, your max mark is 0. If you only do labs 1 to 5, your max mark is 25 on 3. 1 to 5, and then 5 to 9 of the Digital Logic labs, your maximum mark is 2/3 of those available, and then you have a couple of options of completing 1 to 9 and 1 to 3 of Computer Org, or 1 to 3 of Embedded Systems, and you get a max mark of 25, or a project of your choice. It's basically impossible to do them during the lab period. As such, you'll have to do them in weekends, evenings, etc. Facilitate it effectively by a 24/7 lab. And what that means is you're going to have access to a DE2 board that you can take home and use it for the entire term. So basically you can think of some of the labs as pre-labs, and do a couple at home, and then perhaps do one in a 3-hour lab period, or do them all at home if you like. You're not on the email list, then make sure you get on them. I typically use Aurora and Jump, and often you get a email from me. It'll be pretty short notice, but it's your responsibility to be on those lists. We have to determine when the midterm and final is going to be, and it's closed book, and the reason for that is so that it encourages studying. And we'll pick a midterm date that's more or less suitable to everybody in the class. It's sort of a historical overview here of how this course is run in the past, and a lot of it is just to get familiar with some of the terminology. So a little bit of an overview of VLSIC, or VLSI, or ASIC, where ASIC stood for Application Specific Integrated Circuit, and VLSI was Very Large Scale Integration. We'll look at some very basic transistor operation. Of course, that's an MOS transistor. Look at a very basic gate, and basically that'll be just an inverter. And we use the inverter to look at performance issues and whatnot, and you'll see that it sort of carries over to more complicated kind of gate. With respect to the CMOS fabrication, we get a brief overview from someone with expertise in that area, spent many years in the field, and hopefully be able to get them for a lecture or two. We'll look at VLSI performance issues. These are typically related to charging and discharging a capacitor, issues you're well familiar with, and to some degree also related to transmission line types of effects, which you may have a little less familiarity with. We'll look at some basic circuits, some of the CAD tools and the design flow, and these are typically fairly sophisticated algorithms and tools that are used that are brought to bear on these kind of relatively complex problems. We'll look at some alternative CMOS gates, but only briefly, because there's not a lot of them that are of any value. Look at some very regular structures which are used to help manage the complexity. Look at some of the structured design techniques that are around to manage, again, the complexity of the devices that you're trying to build, or the design you're trying to build. We'll look at some integrated circuit faults, some conventional test and design for test, how you sort of handle those types of faults. Okay, so very large scale integration, VLSI is terminology, the basic components of most of today's technology. ASIC stood for Application Specific Integrated Circuit, and more recently you see SoC, which stands for System on Chip, which, as you might imagine, is a complete system on chip, where it includes fairly complicated blocks or modules. Electronic devices, as you know, are ubiquitous, found in everything. Certainly don't have to point out to you where they are, but maybe some a little less so than others. Lots in healthcare, obviously lots in game stations, and automobiles, fuel injection systems, etc. So an awful lot of electronics around these days. Since the development of the transistor, semiconductor technology has grown rapidly. Complexity of integrated circuits grows roughly exponentially. What complexity means here is number of devices. And it's basically follows Moore's law, and here's some examples, sort of sampling, if you like. In 1971, first 4-bit microprocessor, roughly 1,700 transistors. 1990, 32-bit microprocessor, 150,000 transistors. 2002, Intel's Pentium 4, 55 million transistors. At the end of 2005, the technology was basically considered a state-of-the-art at 65 nanometer node. And that roughly corresponds to device size. It might be the pitch of the lowest level metal that you're able to fabricate, but it's really related to the size of the smallest devices that you can fabricate. For example, in the end of 2005, it's a 70 million bit SRAM chip. It's greater than 500 million transistors and a relatively high speed of operation. And there's a little photomicrograph of it, if you like. Very, very regular structure, as you might imagine. And then right in here you'd sort of see, well, deep down there would be the 6 transistor flip-flop, which makes up the SRAM cell. A little more up to date, 400 million transistors for a dual core processor, more than 800 million for a quad core, and that would be in a 45 nanometer process. Here's a couple of images of integrated circuits. This one here is an interesting one. It's 2005-ish from the auto industry. Pressure sensor integrated in with some CMOS logic for processing. So basically the merging of technologies, which typically would have been a little bit different from the fabrication perspective. Very structured micrograph of a CPU here. You can see lots of kind of unstructured logic and lots of very structured logic or regular structures in there. Here's an FPGA, a Stratix 4, and of course it's a very regular structure because an FPGA is basically an array of lookup tables or logic blocks with some memory included. So it's an extremely regular structure. Here's an NVIDIA GPU, 1.4 billion transistors, and different parts of the chip you can see divided up for different types of processing. A GPU, by the way, has lots of processor cores typically, and is sort of like an evolution of an FPGA, if you like, where the basic building block or logic structure is more complicated than what you'd see in an FPGA. Here's Moore's law, sort of spelled out here. He noticed fairly early on, I guess in '65, that the transistor density on integrated circuits is doubling every couple of years. Of course, it'd be very early on in the process when he observed this. This exponential growth in ever-shrinking transistor size results in increased performance and decreased cost. Turing made a similar prediction in about 1950. So here's this little sketch of Moore's law and why you can see it's exponential. It maybe looked linear here, but here we have time on a linear scale and we have transistor count on a logarithmic scale. So it's basically showing transistor count doubling every few years. This stuff up here, where they've gone to basically quad cores as opposed to building bigger CPUs, it sort of follows what I believe is called more than Moore's at this point in time, but it's still been a pretty accurate prediction. And one of the in-class assignments, which you'll answer right now, is why has Moore's law prevailed on the CPU front? I think I've already indicated that, and you should be able to figure that out quite easily. Here's a little a table of a couple of Pentiums, and it sort of just showed that as you went from a 1 core to a 4 cores, speed roughly sort of stayed the same. The technology would change, but the number of transistors went up quite dramatically. If you do want to find out how technology scales, this is the place to look, this International Technology Roadmap for Semiconductors. It's from the Semiconductor Industry Association, and they update it every once in a while. The latest is around 2011. And you can see they make predictions, and sometimes they come through, sometimes they're a little behind, sometimes they're a little bit more aggressive, and the technology hasn't kept up. Here, for example, they were thinking in 2010 you'd have a 70 nanometer node technology, and it's closer to 18. They thought that the big chips would be 6 square centimeters, but they're closer to 5.5. Still huge, of course. And they were sort of looking at the clock speeds going up quite a bit. This is probably a projection from 2006, which really hasn't quite held out either, because the on-chip clock speeds aren't at 15 gigahertz, at least that I'm aware of. The wiring level predictions are one that's probably pretty accurate. Early on, perhaps they underestimate it, and 2006 an improved estimation. This is just a little terminology that we'd like to get familiar with. We're going to look at some different processes. This is sort of what we spend most of our time looking at, how you build the basic transistors or basic gates at a very low level. And this is called the front end of line. Here where all the routing takes place. This is still on chip, a whole bunch of different routing levels connecting up different components, called the back end of line. CAD tools spend all their time here. Of course, CAD tools spend a lot of time here as well. And this is just some terminology. This particular figure shows maybe 5 levels of wiring. It could be considerably more than that. And this would be like a solder bump, back end advanced packaging, and it could be maybe 1,000 I/O on your device. Here's Moore's law, that different representation of it with respect to dollars per basically dollars per transistor, or the price of a transistor. So linear scale in time, again, in an exponential or a logarithmic scale in dollars per transistor. So not too many dollars to build a transistor these days. This time we'll take a quick break and be back in a bit.